Well, before I start, a few words about what we do at MPI. Think about device under test manufactured on wafer. And you really want to do measurements of any type of electrical, or even not electrical characteristics of this device under test. So everything what is between your device under test and measurement instrumentation is our business. When we talk about RF, we provide probe systems, we provide RF probes with integrated cables, calibration solutions. Actually, we help you to collect measurement data for your device under test in early stages, and also the intermediate stage and the final stage of your product life cycle. So for PDK development, for testing your design verification, and we also have solutions for the final test and for some RF components. Well, let me get back to my topic. I have a question to the audience. Please raise your hand, those who try to estimate uncertainty budgets on the measurement data. Wow, great, 1, 2, excellent. Well, the next question was like, have you tried to do it for wafer level measurements? No, because that's the topic. That's what I would like to share with you. Actually, it's difficult to do. It's more complicated. There is a short story of my talk. When I was at the university, I must attend a class of metrology. It was 2 semesters. Everybody hated it, but there was no way to avoid it. And I was so happy completing it. And I said, never again, because I never understood what is all this course about. Now I have to deal with it. And actually, in my opinion, there is no way around. First of all, let us talk a little bit about what is the traceability and why it is so important for our measurements. In a simple word, traceability is an unbreakable chain of mathematical computations which help you to link a value you measure, a quantity you measure, with the physical constants that we know. And this chain is usually established at the national measurement laboratories like NPL here in the UK, NIST in America, PTB in Germany. And this chain is provided by some reference devices like national standards. And we send our instrumentation to this laboratory for the calibration services, like secondary standards, even local standards. So it's a complicated topic, but there's nothing previously existed in this domain for wafer level measurements. But why this is so important? First of all, we share our measurement data. We share measurement data between different laboratories. Laboratories are located over the seas, so different measurement equipment. Data are collected using different software, some accessory parts. Also, operator is an important contributing factor to the accuracy of the measurement data. And what is the main challenge today is that the frequency of the measurements that we need to characterize our device under test increase. At the same time, also, the requirements for the accuracy of the measurements increases as well. And usually when we talk about the confidence in the measurement results, it's a reverse proportional. So the higher the frequency is, that the less we're confident in the data we measure, because it's really complicated to understand what exactly is going on specifically in the wafer level environment. This is an interesting example here. It's a data set presented by a campaign. Different laboratories try to compare measurement results of an exactly same physical device, but measured on different equipment. And here's the comparison. One of the laboratories was MPL here. And this is an example of a measured reflection coefficient of a short standard at the wafer level and the through standard transmission coefficient of it. Can we tell if the data are comparable or not? They obviously look different, right? But is that the same value what we measured? Do we have any problem here? If we have a problem, how big is the problem? We cannot tell it. We don't know. Right? Because there is no reference point for us at first, and we also don't know what are the uncertainty budgets as the measurements. It's a philosophical question. We will never measure the actual quantity of a device under test. We will never know it. But we can measure a parameter and estimate how far we are from the real value. So just think of if I had a chance to get only one parameter, for instance, of transmission coefficient of the through, and if the data were reported with uncertainty budgets or confidence interval for each of the data, we can immediately judge it and say that the 2 measurement setups and 2 sets of the measurement data are comparable. Because Every frequency point here and any value presented here is reported with the confidence interval. And if this confidence interval is overlapping, then the data are comparable or say identical, even if they look different. So computing the confidence interval and estimating the confidence interval helps us to make a conclusion and to build the confidence in our measurements when we report it. Sounds like a theoretical part. But for engineers, it's also a very important practical aspect of it. Because if you present the data with the confidence interval this big to your manager, the manager will be shocked and say like, but why your confidence interval is so large? You can say, well, because this is an equipment I have. You want to make me to measure more accurate? We need a budget to buy a new instrumentation. Think of it. All right. So metrology rate comparison is a complicated topic. First of all, we need to estimate all the measurement uncertainties related with our measurement method, measurement setup, and the instruments used for it. For calibration standards, when we calibrate the system, because we cannot measure uncalibrated data, measurement instrumentation, different vector network analyzers have different hardware architectures, results are different. Accessories involved in the measurement setup, operator impact, I mentioned already, it's complicated. Then also, once we capture all these uncertainties for each of the part of the measurement system, we propagate them through the experiment. It's from calibration process to computing error terms, to correcting of the error terms, and finally computing the final parameters of our device under test, like maximum stable gain or some other characteristics of active devices. And tools which were required is, oh, sorry, I hit the button. Am I going too fast? This procedure is complicated to execute in typical engineering environment. We don't have time for it. We don't have tools for it. And actually, we don't really know how to do it. And it was not possible to do for a very long time. But back to early 90s, when engineers in America looked into developing first RF 40 gigahertz processors, gallium, so mimic devices for gallium arsenide, NIST was also involved in this consortium. And then engineers at NIST realized that actually it's impossible at that time to establish traceability for planar standards. But they came up with a very interesting alternative method. And this alternative method helped engineers to compare one measurement setup to another measurement setup and link this two measurement setup together. If we don't know, and if we cannot establish traceability for a quantity we measured on one particular measurement setup, we can say do our best to complete a measurement set of the data at maximum possible accuracy we know, and share with these measurement results with another partner and help them to correlate their measurement data with our measurement reference measurement setup. This procedure was called a process for setup integrity verification, and it helped engineers a lot to compare measurement data provided from different parties. How this was executed? NIST developed a set of reference elements. They are not standards like we call them, like in measurement standards with very known impedances, but it's a set of coplanar transmission lines with some additional impedances of that, and they call it RM8130. Specified it up to the 40 gigahertz, and also together with this setup, they provided a procedure on how to measure it and how to correlate the data that you acquire in your lab when measuring this device to the data acquired by NIST engineers. And it was a very interesting story with that. Actually, once we had this reference material in the past, we didn't know how to use it. We ordered it. At that time, I worked for Zeus Microtech as a RF application engineer, and I read about this possibility, and I really wanted to link my setup with the NIST setup. We ordered this device, this RM8130, which was very expensive. When we received it, and after I put it under the microscope, I saw that, oh, it goes automatically. So my devices were scratched already. There are some footprints from the probes. And I complained to NIST. I said, well, we've just bought from you a new standard set, but somebody used it before. You sent me the used set of reference material. And the engineers at NIST were so polite, they wrote back a long email explaining that actually procedure involves the measurements, pre-measurements of their devices at the NIST laboratory. And if the devices were not measured, I wouldn't have a chance to compare my data to their data. So how the outcome looks like. Together with this reference material, NIST provided a set of the reference measurement data, different impedance devices embedded on this RF8130. And what was very important, together with the estimate of the experimental drift. They computed and proposed to compute the experimental drift between two sets of the calibration error terms. One is acquired at the beginning of the experiment, and another one, you recalibrate your system at the end of the experiment. And you look into the difference in these error terms. Of course, they're different if your setup is drifted. If your setup was absolutely constant, the difference between these two calibrations is like a unity matrices. But we live in the real world, means that every setup we do the measurements drifts during the experiment, and that's important to quantify this drift. And after the drift is computed, it's like a reference system drift from the NIST, and you repeat the same experiment and measure the same devices from devices on your system. NIST software computes the difference in S-parameter measurements between reference data provided by NIST and the data you acquired on your lab. And what is interesting is that if this difference is smaller than the sum of the measurement drifts on the NIST setup during their experiment and your setup during your experiment, this is the kind of the boundary, means that there is no difference between your data. Even if there are some noticeable variations in the S-parameters between these two sets, if they are larger, smaller than the drift of your two setups, there is no difference. We can't assume that the data are identical. And that helped at that time to compute this confidence interval in your measurement data and report it even without establishing the traceability chain on your measurements. To do all these experiments, you actually need to use the software from NIST, which was written on Rocky Mountain Basics. There are not that many people who understand how to use it today. So also, this reference kit, RM8130, is unfortunately not available today anymore. NIST sold it out. And it was limited to the 40 gigahertz only, so also not applicable for today's applications. But the method is actually good, and you can still use it in your lab. But instead of using the reference material from NIST, you can rely on the commercially available calibration substrates. If you want to link one setup to another setup, the same experiment can be done on the commercially available calibration substrates, which can give you probative cal up to much higher frequencies today. So I don't have much time to guide you through another measurement possible way, which we presented at European Microwave Week. You can find it on the slides. That was in another kind of an alternative. 10 minutes. But I have 2 more matters to explain. Let me just go back to directly to the comparison. These days, we have a powerful software. There are 2 software packages. One of them is developed by METAS. It's a standardization institute from Swiss. And another one is provided by NIST from United States. Both software are free of charge. You can easily download them. They have slightly different computation engines, but they help you to report the measurement data with uncertainty budgets. And here's an example using the software from METAS, which is called VNA tools. And what we tried in this experiment is we tried to estimate possible uncertainties of our calibration standards, which come from the manufacturing process. We cannot establish the traceability, the full chain of the traceability, but at least we can estimate when we manufacture calibration standards. Due to the instability of the manufacturing process, every set of calibration standard can be slightly different, and we know these variations. So VNA tools helped us to compute the possible uncertainty in calibration standards, and we use these input parameters to propagate it through the entire calibration process and plot here the expected measurement results for the transmission line, like insertion loss and return loss, with these uncertainties and compare it with the measurement results obtained on the given setup. And what you can see, if even we cannot compute the measurement confidence interval for the test data, but we have the confidence interval for our model of the standard, and we have already pretty good agreement here. So kind of an applicable method, relatively easy to implement in the laboratory environment. So another possibility to build a confidence interval for your measurements is based on the typical on assessment of the reproducibility of the measurement data. This is a very interesting approach that metrologists use, not in our domain in electrical engineering, but more like in the food industry. In the case when actually you cannot build a traceability chain based on individual components, like a bottom-up, you start with the final product and you look at the deviation in some fixed parameter on the final product. Think of you baking the bread. You really cannot establish the mathematical model from the dough end to the end product, right? But you can estimate some properties of the final product and compare them to each other. This method was proposed also by NPL when comparing the data obtained by different laboratories. And you can look into the repeatability of the measurements on a given setup for high reflection or low reflection S-parameters, high transmission or low transmission parameters. And you can look from it from two different perspectives, for repeatability of the individual measurements or repeatability of the full calibration process. And after you repeated several measurements on the given setup, it's possible to compute the confidence interval based on the standard deviation of measurement parameters, assuming that all the errors are distributed by the normal distribution, so Gaussian distribution. So how it works, and this process is actually applicable also for very high frequency measurements because you simply operate with the data. Here's an example of two possible scenarios. One of them is how to compute the confidence interval for the calibration process when you have the set of different devices, device A, 1, 2, 3, 4, and so on, and calibration processes. Calibration 1, calibration 2, calibration 3, you simply repeat it in a sequence, and you look at the corrected data of one device across the three calibration sets. Or what is also possible to do is look into the measurements of the same device in a sequence, but corrected for only one calibration results. Here's a practical example how we use this method to compare measurement data acquired by 3 different laboratories in a single sweep 220 gigahertz system. Here, where actually there is no metrological solution yet at all. There's no other method can work because that's a very new system, and engineers are still working on understanding all aspects related with the accuracy of the measurements for such a system. But here we see the measurement comparison for 3 laboratories for the same parameter measured for the same device. It's like a reflection coefficient of long transmission line, with the uncertainty budgets computed based on this calibration reproducibility limits. And also corrected S-parameters. There are 3 different data, 3 different laboratories, but with also confidence interval computed on these measurements. It's a practical and relatively easy to use method. Think of you have laboratory A, laboratory B, your partner laboratory. You ask them to do the measurements on the same device a couple of times. Use the simple equation, compute standard deviation, from standard deviation compute confidence interval, and you add it to any S-parameters. And you have an answer. So are your data are comparable or not? Is it an outlier or is it like a typical characteristic that you've measured? And you can do it even further. What I put also on my slides is a comparison for differential devices measurements. Differential single sweep system, which gives you a data measured from 0 to 220 gigahertz. We looked into the measurement deviations or calibration deviations for all 4 ports, and here are like a worst case scenario for different types of the measurements, like high reflection coefficient, low value, small value of reflection coefficient, high value for the transmission coefficient, measurement deviations and the calibration deviations. And we realized that on the same setup we've got value which is so measurement and calibration deviations is about 0.02. It's a linear scale, which is a relatively small number. And based on it, you can compute confidence interval for your data. This is a linear scale, and report the measurement characteristics with the confidence interval. And what is even more interesting, that we could look into the difference, because it's a 4-port system. We can also compute the differential parameters, and we've realized that there is a difference between the single-ended mode and the differential mode, differential S-parameters, and the confidence interval, or say standard deviations for the differential S-parameters, are smaller. So it's kind of an accuracy is higher, which is why we switched the differential device, because it looks like the noise-associated errors are minimized for differential configurations. Good, and now the final topic, traceability. Indeed, there is a traceability chain established now, just since, I think, 2 years. We know how to compute the full traceability chain for planar measurements up to 110 gigahertz. What was the key for this solution is to establish the analytical mathematical model for coplanar transmission lines, including radiation loss and including surface roughness. That was a very important development done, completed just recently. Also understanding what is the dielectric constant characteristics in the broadband frequency range. Previously, metrologists were able to measure it only, extracted it only to the few frequency points, but there was work done at NIST and PTB as well, how to measure dielectric constant for the broadband in the relatively wide frequency range and correlated with the standard methods. And last but not least is an analytical calibration solution, which is implemented in the software from Metas VNA tools, which helps you to collect all this data and propagate them through the measurement experiment down to your device under test S-parameter correction. So as an example, we published the paper. So actually, PTB was the main author and MPI is a co-author, where we demonstrated how to establish traceability chain for the planar calibration to the probe tip and on commercially available calibration substrates up to 110 gigahertz. And the paper was presented at RFTech 100, which is 2023 in Las Vegas. And what is possible to achieve today is, right now is only PTB who has this type of the service. Basically, you can contact PTB and ask them for a traceability report, and they will provide you the measurements of a commercially available calibration substrate with the real uncertainty budgets computed, traceable to the standards at PTB, up to 110 gigahertz. And here this is an example of such a report where we have the standards electrical characteristics from this calibration substrate, including reference elements like symmetrical attenuators with the fully traceable confidence interval uncertainty budgets. This is how this report looks like. A little bit of marketing activity. We reported it at last European Micro Week last year, and the PTB has it on their webpage. We had it also on LinkedIn, and this post went viral. Actually, I had so many comments about this post. This is the first commercial calibration substrate with full traceability chain established. Kind of the breakthrough, but I would say it's just the first step to it, because I need to be careful what I'm saying here. Is a traceability chain like we know it, for instance, for the power measurements or measurement of the waveguide sections? No, because what remains unbreakable is the relationship between the standard and the probe. We can establish traceability chain, but only in the given environment and for the given configuration of RF probe and the standard. If you change the probe, the experiment must be repeated. Unfortunately, there is no way to split these two, the probe from the standard. Today, but that's already a very big progress forward. And this is the outlook for the next couple of years of the work, and engineers are working on it. First of all, is extending this solution up to much higher frequencies than 110 gigahertz. Then understanding what is the contributing factor from probe to standard interface and how to disconnect these two from each other. And also switching it to the on-wafer measurements and actually in your customer environment, because traceability is nice if it's established on a commercial calibration substrate. And believe me, as a vendor of calibration substrate, I would love to sell you for a lot of money a calibration substrate with established traceability chain. But you don't do your measurements on this cal substrate. You measure your own devices. So how to transfer it from well-known environment into your devices, this is the work that still needs to be done. Yeah, this is it. Thank you very much.